When I talk with the directors of other environmental journalism programs, and it's a select few, and we do talk, they often ask about the science reporting class that we offer each spring called Story Lab. And they say, like, how do you do that? How do you pull that off? And what they mean is, how do we manage to put every journalism graduate student into a relationship with a research lab for a full semester every spring? It's super special. And before the how do we pull that off, let me explain why do we bother. Journalists and scientists are both professionally dedicated to confirming and sharing facts. They're both invested in the art and science of verification. And yet we work at dramatically, radically different scales and speeds, and often for very different audiences. So these differences can create tension. Researchers don't always love it when a journalist calls asking them to sum up their life's work in a short interview, or a comment on a maybe tangentially relevant contemporary topic. And it's not always super helpful to journalists when scientists suggest that we just read the recent paper on that. And yet, both professions are working to create a fact-based understanding of the ways the world does and does not work, which brings us to the how. Story Lab is made possible by the personal relationships and interdisciplinary generosity and curiosity of research scientists at the University of Montana. A dozen research labs across campus, and sometimes across our broader community, allow a journalism graduate student to sit in on lab meetings all spring. And over the course of the semester, the journalism students ask questions about how science works, how it's focused, funded, published, put to work. They write about the research, but also about the students in the lab. And those emerging scientists get to practice their communication skills, making their work meaningful to a broader audience. It's a very special part of our campus and journalism's graduate program. I'm grateful to everyone who's hosted a journalism student. Anybody who wants to host a journalism student and hasn't should just give me a call. But tonight's speaker embodies the goals of Story Lab by bringing the worlds of journalism and science together really at the highest level and in the most urgent way. Megan Molteni is on the health and science desk at STAT. It's a news outlet focused exclusively on news about health, medicine, and scientific discovery. She has considerable experience reporting on the gene editing technology CRISPR and genetic privacy issues that surface as big data, big DNA data becomes available beyond the realm of medicine. Read her about that. Reconsider your ancestry.com. Before moving to STAT last year, she led Wired's science coverage of COVID-19 and the pandemic. And it's her work at Wired that brings Megan to us today to discuss the story behind the story, for which she was awarded the 2021 American Association for the Advancement of Science Kavli Award in magazine writing. This is a huge award in the field of science reporting and journalism. Since their inception in 1945, the AAAS Science Journalism Awards have honored professional journalists for distinguished reporting on the sciences, engineering, and mathematics. In recognition of a generous endowment by the Kavli Foundation, the awards are now called the AAAS Kavli Science Journalism Awards. The contest is open to journalists worldwide, and they recognize the best that science journalism has produced each year. Before I hand the podium to Megan, it seems worth mentioning to me that for several years, she worked as a fact checker at Discover magazine. And I think this is an amazing job, and she did it amazingly. It's very exacting, and it's right at the intersection of science and journalism. Imagine that was your job. Imagine what you do after that. Megan's about to tell us. She received a BA in biology from Carleton College and a master's of journalism from the University of California, Berkeley. She spends fall semester in Missoula, so we're very lucky to see her from time to time, and calls Minneapolis home the rest of the time. I give you Megan Molteni.
Thank you, Nadia. That was awfully warm welcome. And hello to all of you. Can you guys hear me okay? I'm going to be hitting the computer, but I'll try to, if you can't hear me, let me know. So thank you for coming tonight. And thank you to those of you who are watching on the stream. I'm really happy to be here to kick off the return of this in-person version. I do have to admit, for me, it's like a little bit weird because this is definitely the most people I've been in a room with unmasked. The last time, I think I was thinking about it, it was 2019 in October, and it was like right next door when Tommy Orange came to town. Great event. But, you know, back then I didn't think twice about sharing the air with a few hundred people for an evening. I know we have less than that, but that's kind of that's where I've been at with my COVID precautions. And back then I didn't really know anything about that thin film of liquid that coats our airways, and how every time we breathe in and those airways open, that film stretches like the surface of a bubble and it pops and it pinches off millions of particles, which we breathe out, and how all those invisible particles hang around in the air, mixing with particles that other people breathe out. And so when you're indoors for any extended period of time, inevitably some of the stuff you're breathing in very recently was in the bodies of the people you're sitting next to. And if any of those bodies happen to be incubating a viral infection at that exact moment, well, some of those viruses are going to be mixed in with all the salts and mucus and other lung goo that make up those particles now floating around the room. So I'm happy to see all the masks in here. This is probably a good time to say if at any point during this talk you feel compelled to put one on, we have them. That would be great. I'm not wearing one right now because I actually have this little CO2 monitor that I carry around with me now, and it's telling me that the concentration of respiratory particles in the air is actually pretty low, pretty good. We're at 679 parts per million, which is green. We'll see if that changes as the evening goes on. May update my outfit, but I will keep you all posted. So it's thanks to some of the scientists I'm going to talk about tonight that we know that things like wearing tight-fitting masks and avoiding places with poor ventilation are important measures that people can take to protect themselves from the coronavirus. But that wasn't always the message that leading public health authorities were communicating to the public. And in some ways, that's like totally to be expected during any period of great scientific uncertainty, like in the early stages of a pandemic. It can take a while for official recommendation to catch up with the evidence, which is oftentimes coming out in a deluge of case reports and the back and other forms that aren't peer reviewed or have been rushed through the peer review process. And an outbreak of novel infectious disease is not just a public health crisis, it's also a crisis of information. And this presents a real challenge for journalists. By choosing what to write and how to frame our narratives, we, more than anyone else, are shaping public understanding of the risks of infection and what can be done to mitigate them. And the stakes are high. Getting it wrong isn't just about tarnishing the reputation of your publication. It could stir people to panic or lull them into a false sense of security. Lives are literally on the line. And what has made SARS-CoV-2 in particular even more problematic is that the way it spreads defies the narrow definition that doctors and epidemiologists have used to divide up the world of infectious disease for the last 100 years or so. And it took a different kind of expertise from physicists and engineers in the field of aerosol science to shine a light on what was really going on. But that opened up I knew I was going to stumble. That opened up an epistemological turf war. That word is tough, which at times turned pretty ugly, and it made things really confusing for us and for the public. And journalists like myself spent much of 2020 just trying to figure out what side of that war to come down on. So tonight I'm going to try to take you inside those high stakes moments as all of us struggled to get it right. When all of this started, I was working as a staff writer at Wired. As Nadia said, I was covering a sort of biological Black Mirror beat, genetic engineering, brain plants, artificial embryos, that sort of thing. And I first learned of this mystery pneumonia that was spreading in Wuhan from a story written by my now colleague, Helen Branswell at STAT on January 4th, 2020. Helen was one of the first people to alert the world to what was going on in China. And I was certainly concerned by what she was reporting. But it wasn't obvious at the time that this pneumonia outbreak was a story for us. Wired Science Desk was small, just 4 reporters, and none of us were dedicated to infectious diseases. And like many magazines that also have digital footprints, we weren't very well set up to cover breaking news. We really had to pick and choose where to put our resources, and we usually put them towards stories that had a clear technology angle. But a few days later, that angle emerged. On January 9th, Chinese state media reported that the mystery pneumonia was being caused by a novel coronavirus, and that scientists had isolated it and fully sequenced its genome. The next day, an Australian virologist tweeted that the viral sequence had been uploaded to a public database, which meant that scientists all over the world could now begin analyzing it and using it as a blueprint for building diagnostic tests. And what struck me was that this was also a big change from the last time something like this had happened 18 years earlier with the SARS outbreak. At the time SARS claimed its first victim in November 2002, the world had no idea that there was any kind of respiratory virus spreading in China. Initially, the government hid the epidemic from the rest of the world. It wasn't until months later that Chinese officials notified the World Health Organization that there was a strange new infection spreading. And that was only after a whistleblower leaked details to the American press. By May of 2003, 2 teams of scientists from Canada and the US had generated the first genome sequence of the SARS virus from 2 people who contracted it outside of China, and they'd identified it as a coronavirus. And so in January of 2020, when I called up Jim Leduc, a former CDC virologist who'd led the American team, he told me that that moment had been a real turning point for them. After that, they could build tests, they could do contact tracing, they could isolate people who'd had the infection, and within a few months, the epidemic had been contained. So Leduc saw in this moment that the fact that China had publicly posted this genome so quickly was representative of a real shift in terms of the country's own advances, in terms of sequencing expertise, which it had invested a lot of money in over the intervening decades. And that was a Wired story. So we published this on January 13th. At the time, my colleagues didn't really know I was paying attention to this. It wasn't really on the radar of anyone in San Francisco. But over the following weeks, I joined a growing group of reporters tuning into daily press briefings held by the WHO to learn what we could about how fast this outbreak was moving and how this virus was being spread. And during that time, we were consistently told that this virus was primarily transmitted through respiratory droplets from the coughs and sneezes of sick people that could only travel about 6 feet. Do you remember seeing something like this? This is advice to clean your hands, soap and water, cover your nose. Does that look familiar? So this is a tweet from the WHO, which was posted on January 26, 6 days after China first reported the coronavirus could spread between humans. Its message was the best way for people to protect themselves was to frequently wash hands, stay away from anyone who's visibly sick. Now, 2 days before this tweet, The Lancet had published a case report of a family who'd contracted the virus while on a visit to Wuhan. And it mentioned something notable. One child who tested positive never developed symptoms. And on its own, it didn't prove anything about whether or not asymptomatic people could transmit the virus, but it raised the question for the first time. And a few days later, another worrying report appeared. This one in the New England Journal of Medicine described Germany's first cluster of coronavirus cases. And what was unusual was that the patients all seemed to have contracted the virus from a colleague who was visiting from China, and she had no symptoms at all during her stay. Now, even in non-pandemic times, case reports are tricky and journalists have to treat them with care. Kind of by definition, they exist because some doctor somewhere saw something out of the ordinary, something that was enough of an outlier that they want to alert the wider medical community. And so the question for us during the early phase of an outbreak of a never before seen virus is, are these truly edge cases or are they harbingers of what's to come? And so to try to answer that, I got in touch with some infectious disease doctors and coronavirus experts to ask about this report. And the people I spoke to agreed these cases were worth paying attention to. But on their own, they weren't proof that our understanding of how the disease spreads required a major update. What mattered, I was told, wasn't that asymptomatic transmission had maybe happened this 1 or 2 times. What mattered was if it was happening a lot. So we decided to wait and see if it was going to happen a lot. Because the epidemiological data that was available at that time wasn't showing that. So the assumption that public health experts were making was that this new virus must be acting like other coronaviruses, that you had to have symptoms to spread it.
Seems to get lost in that question is that, as Bob said, and I agree, we would really like to see the data, because if there is asymptomatic transmission, it impacts certain policies that you do regarding screening, et cetera. But the one thing historically people need to realize that even if there is some asymptomatic transmission, in all the history of respiratory-borne viruses of any type, asymptomatic transmission has never been the driver of outbreaks. The driver of outbreaks is always a symptomatic person. Even if there's a rare asymptomatic person that might transmit, an epidemic is not driven by asymptomatic carriers.
So that was from a White House press briefing on January 28th. That was Tony Fauci, the head of the National Institute for Allergies and Infectious Diseases. And he addressed that question of asymptomatic spread, and pretty unequivocally. So we made the decision not to write something about that report from China or the one from Germany. And a few days later, Science came out with a story that threw that latter report into question. The researchers a reporter at Science had learned hadn't actually spoken to that index patient, the woman who had traveled from China, but another group in Germany had, and they had learned that the woman began to feel unwell during her travel back to China. WHO scientists piled on, calling this study flawed, and their experts also made a point in briefings and interviews to draw this distinction between asymptomatic and pre-symptomatic transmission. It wasn't that people who never felt sick could be contagious, they said. It was possible people could spread it before they started to feel bad. But even that, they said, like Fauci, was very, very rare. So outlets that had reported on this series of developments did the responsible thing, and they updated their stories. This is from my now colleague, Drew. And they also wrote new ones. And so from where I was standing, that episode seemed to validate our approach, which, we had sort of made by necessity, but that we were going to wait and see and synthesize. We hadn't raised the specter of asymptomatic spread only to have to walk it back. But new evidence kept emerging that was getting harder to ignore. Numbers out of China continued to rise steeply, including reports that lots of healthcare workers were falling ill. And by the first week of February, more than 24 countries had also reported cases. And the next week, a well-regarded modeling group at Columbia put out this preprint study suggesting that the rapid spread that we were seeing around the globe could only be explained if there was much more asymptomatic transmission going on. And then there was the cruise ship, the Diamond Princess, quarantined in Tokyo Bay for most of the month of February. Upon arrival at the port, Japanese health officials tested people who were showing symptoms, and they found 10 cases initially. But when they changed their policy 2 weeks later to test all passengers who'd been isolating on board, the number of confirmed cases rose to more than 700. And about half of the people infected in that outbreak showed no symptoms at the time of their test. And that proportion was substantially higher than had been reported anywhere else. This was potentially a very big deal because it raised the possibility that there were actually many more infections that were going undetected. And if truly asymptomatic cases were playing a more substantial role in transmission, that would change what kinds of public health interventions would be most effective. To go back to what Tony Fauci said, asking people to stay home or wear a mask if they were feeling ill wasn't going to be enough. That this was a real possibility only hit home for me when I heard Nancy Messonnier of the CDC say this during a press call on February 25th.
Of income. I understand this whole situation may seem overwhelming and that disruption to everyday life may be severe, but these are things that people need to start thinking about now. I had a conversation with my family over breakfast this morning, and I told my children that while I didn't think that they were at risk right now, we as a family need to be preparing for significant disruption of our lives.
So until that moment, the coronavirus had felt like a thing that was happening somewhere else to other people. I and the other science reporters had kind of been casually tuning in and out of the outbreak while still writing about other things. There was the first CRISPR trial for cancer that came out with data. Permafrost thaws were opening up sinkholes in the Arctic. There was a lot going on. But now it had our full attention. And that was why it was sort of confusing not to see any shift in the guidance from the experts we were turning to make sense of all this new information. The WHO was still pushing hand washing as the best way to protect yourself from infection. And that message was spreading, thanks in part to catchy TikTok PSAs like this one, which I'm about to play, produced by Vietnam's National Institute of Occupational and Environmental Health. Club banger aside, that disconnect was very jarring to me because I was still learning something that much more seasoned infectious disease reporters already knew. And that was that risk-averse health authorities like the WHO don't change their recommendations overnight, and they don't change them lightly. As a global entity relied on by governments all over the world for guidance on how to keep their healthcare workforce safe, the consequences of a false alarm would be severe. So the evidence that telling us like how much people are breathing out, and it's a useful proxy to understand, you know, if you're breathing out CO2, you're breathing out other stuff. And so if you're in poorly ventilated places, like if we were in a smaller room or a place that had fewer changes of air per hour, we'd start to see the numbers go up. But how it detects CO2, I don't know. But I know people who could tell you, and I can send you a link. So, okay, where were we? Yes. So if the WHO was going to change its recommendations, they were going to need like really clear and compelling evidence. And the problem with that is that it's much easier to collect evidence of symptomatic spread than asymptomatic spread, right? So people feel sick, they go get tested, go to the hospital. People who have the virus growing inside them, but otherwise look and feel normal, they're not going to be so easily identified. And so detecting stealth spread, you know, requires one of two things. You can either do intensive contact tracing and sequence those genomes so that you know that those cases are related, or you can do mass screening, just like test everybody. But neither of which most public health agencies were set up to do in the early days of the pandemic. And the places that were, so this was like Singapore, Taiwan, other places that had been through SARS, provided the best early evidence that asymptomatic transmission was happening, in addition to what was going on that cruise ship. But compared to the data that was coming in from China and Italy, which was mostly coming from hospitals where they were seeing really sick patients, like the asymptomatic data was a trickle. And so that detection bias made the relative importance of asymptomatic transmission harder to see. Because what we know now is that 1/3 to 1/2 of people infected with the coronavirus never experience symptoms. But at that time, there was also compelling reason for the WHO to wait until more definitive data arrived. And that had to do with logistics. Due to most of the world's medical masks manufacturing being based in China, large parts of which were now locked down, a global mask shortage was underway. And while countries like Taiwan had jump-started domestic mask manufacturing in the early days of the outbreak, and they were handing them out to citizens as part of the universal masking strategy, most Western nations, including here in the US, had slow-walked shoring up those supplies. So our public health authorities wanted to make sure that the limited supplies we did have were conserved and prioritized for healthcare workers who had the greatest exposure risks. I don't know if you remember this. This is a tweet from our then US Surgeon General. This was on February 28th. I don't know, for those of you that remember this, like, did you find this confusing? Okay, yes, there are nods. I found this very confusing, right? Because it's like, if masks are not going to be effective at helping me or you avoid the coronavirus, like, how's it going to help doctors on the front lines? And so this would go down as one of many, I think one of the worst, but there were many to choose from, messaging mishaps that US health officials made in the early days of its pandemic response. And what they were trying to communicate, which Tony Fauci would later tell my colleague Adam Rogers and I, was that most people were at pretty low risk of coming across the coronavirus in their everyday life. So you didn't need masks just because like the risk was low. And that by buying them, they were taking away from people whose risks were high, like healthcare workers. But what people heard because of this messaging was that the nation's top health experts didn't think masks were of any benefit. And in fact, the case for masks, not just for healthcare workers, but for everyone, was about to get a lot stronger. So March 4th, less than a week later, JAMA published a study that found genetic remnants of the virus stuck in the air or stuck to the air vent blades high up in a COVID-19 patient's room in Singapore. They didn't find any virus in the air itself, but a second study from a hospital in Wuhan, described in a preprint a week later, did, although only in trace amounts. But NIH virologists, actually just down the Bitterroot at the National Lab in Hamilton, reported in another preprint on that same day that SARS-CoV-2 could remain infectious as aerosols for at least 3 hours under artificial lab conditions. Now, none of these were very strong pieces of evidence on their own. Like, what was still undemonstrated was whether or not infected people breathed out aerosols laced with enough virus to cause infections. As one of the NIH researchers on that third paper said on Twitter, like, they had not provided evidence of aerosol transmission. But taken together and coupled with what scientists were learning about asymptomatic spread, the study suggested that coronavirus might be behaving differently than how it was being described by leading public health authorities. So large droplets, remember, come from coughs and sneezes, right? But no symptoms means no coughing, means no droplets. And so if asymptomatic people were spreading the disease, they had to be doing it another way. And aerosols, that much smaller particles that everyone generates while breathing and talking, were starting to look like a likely culprit. Oh, I know. Got these out of order. Let's go here. And if that were true, so this is a really useful illustration from Don Milton, who's an aerobiologist at the University of Maryland. And so the ballistic drops, that would be what we call like a droplet. That's the thing that kind of shoots out like these bigger droplets that we're talking about. Everything else would be different shapes and sizes of aerosols. And so the smallest ones, the red ones, are the ones that can penetrate deepest in the lungs. The yellow ones, kind of the middle size, can go further down or not as far down the respiratory tract, and the green ones get caught up in the nose. And so these were the types of particles that were starting to look like, the likely culprit of this asymptomatic spread. And if that were true, N95 masks, which filter out even these small aerosols, would be a more appropriate precaution for healthcare workers and other people with lots of exposure to the virus. But even looser fitting surgical masks could still cut down on the risk of infection if everyone wore them. Not so much by stopping the virus from getting in, right? Because they have these gaps around the edges, but by stopping it from getting out. So you see how even the small particles, kind of wind up more contained behind these masks. And ensuring the flow of fresh air would also dilute those smaller aerosols. I'm going to go back to that slide that I meant to get to earlier or later. So this new data supported the idea that people should take precautions like increasing ventilation. As Joseph Allen, a Harvard public health researcher who studies indoor air, told my colleague Greg Barber in his story about these 3 studies that I mentioned. But the World Health Organization had a different read on that data. And at the time, their take was that at that time, there was no need to change its recommendations. This is from Maria Van Kerkhove, WHO's technical lead for the coronavirus response, right after those studies came out. So many dedicated health and science reporters reported on these studies really carefully with all the appropriate caveats. But some news outlets that didn't have those kinds of people on staff reported the findings without as much context or nuance. And so unsurprisingly, the message that was soon spreading on social media was that COVID is airborne, like in the movies. And so for the weeks before this, WHO officials had been working with companies like Twitter and Facebook to combat misinformation about COVID-19, which was just like flying around like crazy back then. So they'd flagged just wildly untrue claims that like the coronavirus was created as a bioweapon or that you could cure it by drinking bleach. And to that list, they added the claim that the coronavirus was airborne. So this is a tweet from March 28th. And so they've highlighted a visual that was going around on Twitter and, stated very clearly as a fact check that COVID is not airborne. And this was a very influential in how we approached this issue of transmission. It kind of anchored our understanding even as new information was coming in, because the last thing we wanted to do was overinterpret the evidence and like add to this infodemic. So at that time, we as reporters made the decision that we would, stick to this official guidance and our coronavirus coverage, which was increasingly kind of providing advice for what people should be doing to keep themselves safe. Meanwhile, over on our opinion section, which is called Ideas at Wired, we had other writers who were churning out more contrarian takes like this one, which called on Americans to take up universal masking. And this wasn't unique to Wired. This was a similar dynamic playing out in many other newsrooms, the Times, the Post, and the Globe. The opinion pages became the place where critical conversations about existing public health policies found some room to run. And the ones that advocated for speeding along herd immunity by just letting the virus rip obviously didn't age very well, but others turned out to be right. The thing was, though, that like in March of 2020, running them created this internal consistency between our opinion pages and our reported stuff, and at times that confused our readers, inflamed our sources, undermined our own reporting, and led to a bunch of fights on Slack. But on the other hand, it also, that freedom to kind of go beyond the guidance also allowed writers like Roxanne Campsey to explore a semantic squabble that was coloring this whole question of transmission. She wrote this really important story in March, pointing out that when health officials were saying the coronavirus isn't airborne, they were deploying a very narrow definition of the term. And that definition, handed down to doctors through decades of medical textbooks, said the virus is only truly airborne if it infects people through aerosols that hang around for at least half an hour and travel across long distances, like across a room this size or multiple floors of a building. And the only kind of aerosols that do that, according to this definition, are the finest ones, the ones that are smaller than 5 microns. Anything bigger is defined as those droplets we talked about. And in the world of healthcare, the distinction between droplet and airborne transmission has enormous consequences. If a pathogen is considered airborne, patients have to be put in expensive isolation wards. All medical staff need to don more intense PPE, including N95s. But scientists from the field of aerobiology who study the physics of these particles told Campsey that in reality, things were not so black and white. And that meant that when public health officials say a pathogen is or isn't airborne, she wrote, they create a false dichotomy that doesn't keep people safe. I'd never heard of the 5 micron distinction before, or the fact that there was an ongoing debate about its scientific merits. But once I started paying attention, I noticed it everywhere, especially on Twitter. Because that's where aerosol scientists were posting new studies and case reports that supported the idea that airborne transmission was in fact driving the pandemic. So I started reading everything they were talking about, investigations of outbreaks that didn't fit the pattern of droplet spread, like this one at a call center in South Korea and a choir rehearsal in Washington. And I started following all the people who were pushing back on this idea that if it were truly airborne, they said lots more people would be getting sick than what the epidemiological data was showing. Imprecisely using the word airborne, they complained, was fomenting panic. Now, I was kind of following all of this in the background as I worked on other pressing pandemic stories about like vaccines and treatments and what the virus does to our brains and our hearts and our children. And so those first few months of 2020 were, just the busiest I've ever been. But as spring became summer and the CDC broke with the WHO and began recommending people wear cloth face coverings, we started to give more space to this transmission debate in our coverage. So I wrote about the role of aerosols in meatpacking plant outbreaks. My colleague Adam wrote about how researchers were studying how the virus moves, both at the micro and macro scales. And we teamed up to write about how that work was informing the modelers trying to predict when and where the next COVID waves would crash. And by June, when the national attitude had weirdly swung toward majority pro-masking, even in the White House, he and I decided to take another good hard look at the science of viral spread. And one of the people I called was Lindsay Marr. She's an aerosol scientist at Virginia Tech who'd also been studying respiratory pathogens for the past decade. And she told me she'd been convinced there was enough evidence of airborne transmission way back in March, like middle of March, as soon as she saw that Germany cluster report. And that actually she and 35 other aerosol scientists had laid it all out in an email to the WHO. And that when they were invited to meet virtually a few days later on April 3rd, that group of doctors and researchers who advised the WHO on infection containment pushed their concerns aside. The evidence, they said, was still too weak. Mar disagreed, and so she had signed her name along with 238 scientists to a letter calling out the WHO's missteps and urging it to revise its recommendations. And the letter, I learned, was to be published the following week. So Adam and I broke that news on July 2nd. And like a typical magazine story, even on the web, it was buried about 2,000 words in. I don't think most people got the message until 2 days later when the New York Times ran their headline, which obviously put it all out there a little bit more clearly. But even as this was happening, I was thinking about something else that Mar had told me that seemed like maybe an even bigger story. She had a hunch that the real reason that she and her colleagues had not been able to break through to the WHO advisors was that they had been operating under a false idea about how aerosols and droplets behaved, and that idea was rooted in the medical community's outdated 5-micron definition. Somewhere back through the decades, someone had gotten that size wrong, she said. And that error had led to the incorrect idea that diseases spread through aerosols were rare bugs, the exception to the droplet rule. But in fact, they were quite common, she believed. And so the fact that droplets had been blamed for so much human suffering was an artifact of history, not a law of nature. And Mar didn't know where the error had come from, but she told me that she'd begun a search to find it. And she'd even enlisted the help of a medical historian. Her hope was that by clearing up the error, she could clear the way for preventative measures against aerosols to become a pillar of public health policy. I asked Mar if I could follow along. After some back and forth, she said yes. The first person she introduced me to was Katie Randall, a student of medical rhetoric with a specialty in citation tracking. And she told me that most of the WHO material she'd found describing the 5-micron cutoff didn't cite a source. So she'd had to dig up other clues. And through her research over the next few months, I learned just how long epidemiologists and aerosol scientists had been talking past each other. Started back with this guy, Karl Flug. I don't know if I'm saying that right. A German bacteriologist who was the first person to write about droplets as infectious agents. In the late 1890s, his lab placed agar plates in rooms at various distances from talking, coughing, sneezing tuberculosis patients. And then they were able to show that respiratory particles containing contagious bits of the tuberculosis bacteria tended to settle on the plates that were within a few feet of the infected individual. A decade later, an American public health researcher named Charles V. Chapin referenced this work in his influential book, Sources and Modes of Infection. In it, he observed that respiratory viruses were spread most easily when two people are in close proximity. Only rarely were such diseases transmitted across very large distances. And he concluded that Flug's droplets, which had only traveled 2 to 3 feet, were therefore the most likely means of transmission. However, he admitted at the end of this very long book that this was an inferential leap, really without any evidence behind it. But his thinking went, if people were afraid of germs, that germs were in the air, it would fill them with a sense of nihilism, and they wouldn't do things that he had found to be effective in his hospitals, like distancing and hand washing. The views that he wrote in this book would go on to become the bedrock of public health policy in the US for the next century. But there was a problem. In their seminal experiments, Flug's team had waited for up to 5 hours before removing the agar plates for analysis. They had understood that finer particles would need that long to settle out of the air, and they wanted to capture them too. So what they had described as droplets weren't just large particles that fell quickly to the ground. They were also aerosols. But Chapin either didn't notice that or did and misrepresented it anyway, or maybe his German just wasn't very good. Either way, the clinical and public health communities began running with this notion that only large, visible liquid droplets matter for most respiratory diseases, and it soon became doctrine. But hand washing and distancing didn't totally rid early 20th century societies of diseases like tuberculosis and measles. And by the 1930s, a Harvard sanitary engineer named William Firth Wells and his wife Mildred Weeks Wells on the outsides, who was a physician, had become convinced that transmission was happening via aerosols. And to prove it, they first tried exposing rabbits to aerosolized mists of tuberculosis bacteria. The bunnies that got dosed with the bigger droplets stayed healthy, and the ones that got a fine spray, aerosol smaller than 5 microns, fell ill. But public health leaders at the time, like Alexander Langmuir, who was the first director of the newly formed US CDC, didn't find this convincing. Let's see. There we go. So the Welleses tried other things. Working with another colleague named Richard Riley, who's the one in the middle, they set up a guinea pig colony in the penthouse of a hospital directly above a specially prepared tuberculosis ward that vented air right into the penthouse. And through a series of meticulous experiments conducted over 4 years with hundreds of animals, they showed that tuberculosis did indeed transmit through the air. And their results were published in the late 1960s after Wells died due to cancer. And it was only after that that influential people like Langmuir started to come around to this idea. In 1963, he told a crowd of public health researchers at a meeting in Kansas City that particle size is a major factor in the occurrence of airborne infection. And he specifically called out particles smaller than 5 microns. And he wasn't wrong, like at least where tuberculosis is concerned, because the tuberculosis bacteria can only infect cells deep within the lungs. So the only time you see an infection is if it hitches a ride on a particle small enough to get down there. And the only particles that can do that are smaller than 5 microns. But particles bigger than 5 microns can be inhaled, and they can get into other parts of your respiratory tract, like we saw in that earlier illustration. And other kinds of bugs aren't as picky. The flu, coronaviruses, they can cause infections higher up in the respiratory tract. So in some of his earlier work, before he got into like dousing rodents with tuberculosis, Wells had actually used novel air sampling technologies to calculate curves that showed how fast respiratory particles of different sizes settle out of the air. And his model showed there was kind of this like critical moment where if they were of a certain size, they would have this kind of ballistic trajectory. And if they were smaller than that, they kind of hang around in the air. And it kind of led to this dichotomous classification between these two sets of particles. But according to his calculations, that crucial size threshold was around 100 microns, not 5. And it wasn't fixed. It depended on humidity and airflow and a bunch of other factors. And so as Katie Randall combed through a century's worth of scholarship, she realized that somewhere along the way, epidemiologists, including the head of the CDC, had taken Wells's work that showed what sizes of particles could float and be breathed in and conflated it with the size of particles that can reach deep into the lungs. And when you adjust to the correct size, what you realize is that the majority of what is coming out of people's mouths are actually aerosols. So droplets, in order to infect you, they have to land a direct hit, right? In a mouth or an eye or like some other mucous membrane on your face. And there's so few of them and the targets are so small that scientists studying them in the lab find they rarely hit their mark. Aerosols, on the other hand, are produced in much greater volumes and they're much easier to breathe in. So this error wasn't purely esoteric. It had led the medical community to be more worried about droplets than they should be and not worried enough about aerosols. On April 28th, 2021, more than a year after Marr's first meeting with the WHO, she and Randall and their collaborators posted a paper describing what they've found. 2 days later, a page on the WHO website about COVID-19 transmission got a small update. The new text still emphasized, you're not gonna be able to read it, but I'll just tell you. The new text still emphasized that transmission happens in close proximity, but it added that it is likely aerosols as well as droplets that's driving spread. And with those few sentences, a century of public health convention was shaken loose from its foundation. Now, that would be a convenient ending. It's where my story ended. But of course, the real world is messier. Improving ventilation and air filtration in public places like schools and offices and government buildings is still very much an uphill battle. Although I will say we're down to 565, so ventilation here, great. The White House recently elevated this issue. They have a clean air in buildings challenge, and just this week they held their first summit on indoor air quality. But that knowledge still has to be turned into action. Many state and local governments don't know there's money available to make those improvements, or they've used them for other projects. And the push to modernize the medical community's understanding of disease spread and to agree on the most accurate words that scientists across fields use to describe it continues today. Which brings me back to this now infamous tweet. Last week, Twitter's support attached a note to it, saying that scientific understanding of COVID-19 had evolved to show that aerosol transmission was indeed happening. In the platform's own words, this tweet provides false information that was not conclusively proven at the time and is now confirmed false. I don't end with this to do some kind of like victory lap or like extract any sort of apology from public health officials. They have the incredibly difficult job of making black and white recommendations when the data is as gray as can be. And although I chose to focus my story on one particular group of scientific underdogs, I think it would be a mistake to view this as a straightforward heroes and villains narrative. In reality, it was about a lot of people wading through a lot of uncertainty, all trying to do their best with the information they had at the time, while lacking a common language to effectively put their respective pieces of the puzzle together. Still, I've told you all this tonight because I think understanding why in 2020 the planet's top public health authority got COVID spread so wrong wasn't something that could be figured out overnight or over a week or even over a month, but it was worth getting to the bottom of. Because of what it has to teach us about the structural weaknesses at the heart of the scientific enterprise and what happens when those weaknesses are exposed. Researchers squirrel knowledge away in field-specific silos, accumulating evidence into a shared understanding of how molecules and viruses and people behave. There can be bad nuts, studies that are flawed or their interpretations are, and errors creep in. Decades might go by before a new technology or an insight from another research field reveals the rot. But by then, so much has been built on top that dislodging this long ago blunder threatens to topple the whole thing. Learning something is easy. Unlearning something is much harder. And as science journalists, it's our job to interrogate science as the human endeavor that it is, a product of history and a constant work in progress. So I just want to leave tonight with some ideas about how we can do better. Other people have had these ideas before. This is nothing, this is nothing wildly revolutionary. But they include thinking hard about our own biases and the biases of the information sources we seek out. What exactly are these people experts on? Are there other forms of expertise worth seeking out? Getting used to uncertainty and communicating it clearly. I think, remembering that the absence of evidence is not the evidence of absence is really important. And you really want to ask questions about what data isn't being collected and why not, and how would the story be different if we had it. And then finally, update our priors. Evidence has to be constantly reassessed, recontextualized, and reinterpreted, and follow the weight of the evidence as it shifts. So that's it. Thank you so much for being here. I believe we have time for like a few questions. There is a microphone over there. I think there's someone monitoring the stream for questions if we have, and I'm happy to answer anything.
Thanks. What a journey. Oh my God. I'll throw it open to you all for questions. Indeed, Lee is monitoring the screen. If you've got questions, holler. Anyone would like to open it up with some questions? I think this is a fascinating journey that we were all along on and we didn't even know it. Questions out there? Yeah?
I have a question. There's a lot of talk about what do you think your role as a
Yeah, that's a really good question. I think we have I think people we don't want to paper over truth, right? If agencies are screwing things up, we have to hold, those mistakes to account. And I think at the same time, you have to be really clear about why were those mistakes being made? Like, are they malicious, or are they because like science is hard and it's changing all the time? And so I think part of our job is also, the one thing that I take really seriously is like trying to inject all my coverage with aspects of like how science is actually done. And as I think, most Americans can't name a like living scientist, or no one. And so I think there's an idea that, just like knowledge comes down and here it is. And so I think we have a responsibility to kind of open a window into how people generate knowledge, and be really clear about what the limitations are. And, I think it would be nice if we, had a little help from our primary education system to be able to like have a little bit more scientific literacy. But I think, that's our job, is to, I think, make it as accessible as we can, because I don't think you can have, people they're not going to trust something if they don't understand why it is. You can't just tell them it's a certain way. So I think you have to really explain the process.
We got a question from the streaming audience.
I've got a streaming question.
Stream me.
So how do journalists know what their the certainty level of their research is, and what the probability of them being wrong might be? And how do they communicate that to readers?
That is the whole business. So I think, within an individual study, there are things you can do to look at to see, to assess like the strength of that evidence. So that might be trying to understand how many people were studied, to look at the methods and say, is the question that they're asking actually supported by the data that they're collecting, or could it have been confounded, by these other things? You also want to look at the people who publish that, at their publication record, like, do they have experience in this? Or are they just parachuting in? That might raise a red flag. But the primary way is just calling people who know much better than you and asking them. I think we all have Rolodexes of people that we can ping when new stuff comes out and say, hey, like, gut check, like, does this pass the stiff test? Or to get a sense of like what the limitations are. And then the other thing is kind of placing it within the broader literature. So if it's something that kind of, fits along with other pieces and it makes sense, then you have a higher, you can have a higher sense of certainty. If it's something that's like completely goes against the grain, it doesn't mean it's wrong. It just means you have to be a little bit more skeptical. And then I think when you're asking people to weigh in on it, you also want to make sure where those people are coming from and what their biases might be. So are they publishing on like a rival hypothesis and like they have a reason to like, swat this one down? You want to kind of have that in the back of your brain. So I would say you kind of have to do all those things. And then you have to say like, hey, everybody thinks, you have to kind of find a way to describe that level of uncertainty. And it's like, hey, most of the field thinks this, but there's a good reason why this thing could be true. And if it doesn't pass the sniff test, you just don't write about it. Also.
There's always that.
Thanks
Yeah.
so much.
Oh, sure.
Obviously, you could say a lot about how the political environment complicated the public health message, but I was wondering if you could talk about how the scientific environment complicated it. You got a lot of preprint articles, you got a lot of updates on Twitter. So other scientists themselves a little bit to blame.
That's a good question. I think everyone carries, a little bit of blame. Something really interesting about this is, so a lot of this, as you mentioned, like a lot of this was playing out on Twitter. And if it were not a pandemic, I was thinking, if it's not a pandemic, would this be happening, like in behind the closed doors of a conference, or, across the pages of journal articles, people writing letters back and forth. And when I asked this of some of these scientists, they said, well, but we'd never be talking to these people. Like, if I'm an aerosol scientist, there's never a doctor at any of the meetings I'm going to. Like, we're not there, like the journals I publish in are not the journals that they read. And so we really got the sense that this like, crazy crisis, which like moved everyone into this, like digital town square that is Twitter, kind of brought together people who like maybe never would have interacted otherwise. And so in some ways, I think that's partially why there was so much antagonism, was because these people were not used, they didn't have like that collegial relationship you have with people in your fields. So I think there were ways that it harmed the dialogue, but there were also the fact that it was happening in the first place, I think felt very novel to this moment. Yeah.
Great job. My question refers to the publication, right? This is a fast moving endeavor. And so publication so quick, the peer review process, I would imagine, was fast. Were there a lot of retractions or any publications that came out there and come back and said, wait, that rule law?
That I mentioned here tonight. I don't think, none of the ones that I mentioned, there were a lot of there were lots of retractions. I don't believe any of the ones I mentioned tonight did. And actually that Germany cluster report that kind of was called flawed, like that wound up being, I mean, that totally bore out. Like they did the genetic analyses, they found out that those clusters had all been infected by this one person. So, there was some nitpicking about how they had disclosed, kind of what they knew about that situation. But that wound up, that's still in the New England Journal of Medicine, and certainly, as we saw, bear out. But no, I think it was for a lot of reporters, it was their first time ever encountering preprint servers. I talk about it explicitly. That's when you are putting something out before it's been peer reviewed, and some of us science reporters have been using them already before, because you can kind of get scoops on stuff. But it really, all of these journalists, including people who've never done science reporting on preprints, where you don't have reviewers writing comments and you don't have people weighing in, that definitely fueled a lot of this reporting that generated kind of a lot of lacking nuance and just like bad takes. And a lot of preprints did either never get published or were retracted later. And some of the ones I'm thinking of tended to be more about like an early one that said the coronavirus had evolved in a snake. And there were like, I don't know, there were a lot of people writing. It's a lot of stuff at the beginning. So yeah, none of the pieces I mentioned. I mean, the Katie Randall and Lindsay Marr publication that was initially came out as a preprint, but it has since been published in the Royal Publishing Society. And yeah, and it has spurred a lot of additional scholarship on top of it since then. Stream.
The stream has questions. Apart from COVID, are there other examples that you know of where the expert consensus has got it wrong? And what was other sort of combat?
Well, I can just say one thing that immediately comes to mind is there's a pulmonologist at the NIH who studies tuberculosis, and while all of this was happening, he went back and did this heavy review of all the data on other respiratory viruses. So like tuberculosis, measles, flu, like a whole bunch of them. And when he looked at what scientists had actually done, he saw in this like meta-analysis that like there was no evidence for droplet spread. And so like he wrote a study saying like all along it has probably been aerosols, and we have lacked the ability to differentiate those like mechanistic transmissions in this close contact 2 to 3 foot area. And so I do expect that in the next couple of years we're going to hear that like other respiratory viruses are actually the current terminology that people are toying around with is called short distance airborne, short range airborne. So that's, you're still close by, it's still close contact, but it's recognizing that's not droplets, it's like aerosols that you're breathing in. And in terms of like other big paradigm shifting moments, I'm sure there are lots of them. I'm blanking on them all right now.
Someone on the screen said the reusable rocket.
Sure. Yeah, I mean, like these things happen. These things happen all the time. What are some? Yeah, I don't know.
There was a strong consensus that cancer was spread by germs in the air, and it influenced the architecture of early cancer hospitals, which were made to spread people out and prevent contagion. And in fact, time came by.
Yeah. Well, I mean, before flu came out with its droplets, the reigning paradigm was that it was in the air. It's called miasma. And so when scientists discovered that there were, germs and microbes, and then he's like, oh no, they're not in the air, they're in these little droplets. Like that was actually overturning kind of the previous paradigm that, was viewed as this kind of, like medieval sort of fear of the air. So yeah, I mean, there's a pendulum to these things, like as new technologies come out and new data emerges.
Do a couple
Yeah.
more and-
Like when there's so much like new data, news, like advice, like P64, like how do you know like what to report on and what to like hold off on and be like, oh no, wait, so there's more. Like how do you know like what you should be reporting?
Yeah, I mean, I don't have any of my Slacks since they took them back when I left Wired, but we had a lot of conversations like, okay, today we have enough information to say you should be doing this thing. I think one of the things we struggled with is there's this precautionary principle, right? Like, so what are things that you could be doing, even if the evidence isn't super strong that it's the right thing, but you could go above and beyond and do it, and you're going to be safer, but you're also not hurting anyone else. And so during that, those early days where there were the PPE shortages, like mask buying for yourself was out. And when we started getting the sense that like 6 feet wasn't going to be enough, I think my colleagues and I, by then we were already like in our apartments at home, personally. And so we're just, not going indoors in buildings or getting all our groceries, on curbside. In terms of like what to report to the general public, I mean, I think that's the whole, we just had lots of daily conversations about, can we go beyond the guidance, or like, do we have to stick with it? And I think once we started to hear that, most scientists don't love to be called up and like asked about their opinions on like breaking news. But when scientists start like reaching out to you and saying, hey, I think something is wrong here. Like, I think we need to be doing something different. Like, I think they're making a mistake. Then you start to pay attention. And when it's not just like one random guy on his couch, but it's like people from MIT and people from Columbia, and they're like, hey, like we think we need to pay attention, then I think that starts to raise the temperature and kind of like make us make those decisions to go out with it.
One last question to take us out. Anything there, Lee? Rob Cheney, take it away. Our last question.
So I just did one of my regular scan cleanouts of all the magazines that I have. Just 2 days ago, and read your story. Seeing you here in person, gives me the opportunity to say I was one of the best whodunit multidisciplinary science trackdowns of how information gets done wrong and how hard it is to put that together right I've ever read. For anybody who I want to put that kind of story together, and I want to say that.
Thank you. That means a lot. Obviously I did not do it alone. I had wonderful editors and wonderful mentor and my friend Adam. So thank you. All right.
Fabulous. Thanks, Megan.